let's get started, okay? The blockchain. Okay, let's talk about the most common blockchain in the world. We're talking about Bitcoin, of course. Okay, Bitcoin is the most common blockchain in the world. And how Bitcoin works is like this. You have, let me see what parts to simplify and what not to do. Okay, you have various blocks. Okay, a block is just a chunk of data, right? Of specific data. And what is that? What does each block contain? Well, each block contains a link to the previous block. Okay, and that block contains a link to the previous block, and that block. And you know, right at the start, there is what's called the Genesis block, which is the very first block that was ever used on blockchain. And its data, no one knows where it comes from. Maybe it's random data. Maybe it's got a secret message inside it. We don't know. Okay. So anyway, there's the Genesis block right at the start, all the way. Okay. But so each block contains a link to the previous one. Okay. Each block contains some transaction data as well, or actually a set of transactions. Okay. Saying, you know, send from A to B, let's say. Okay, so A is what's called a wallet. Okay, every wallet has got a specific name. The name is given to you when you actually set up your Bitcoin wallet, and it's something. It's, you know, this, like, I don't know how many characters long. Just, it looks like gibberish. Just a string of gibberish. Okay, but that's your wallet. And so when you send some number of coins or parts of a coin to B, then you know, you submit that to the blockchain. Okay. One of the ways of doing that is by okay, you take a step back. You submit your transactions to the network, okay, to the Bitcoin network, and your transactions get sent over to miners, okay, who mine a block. Now, what does it mean to mine a block? It means to solve a really, really, really hard problem. And after you've solved the problem, then you basically put your hand up on the network and say, ha! I've solved the problem, and this is the solution. And then some problems are really, really difficult to solve, but it's easy to see that they're right. Okay? Like, for example, think of a 50 million piece puzzle. Okay? And you know, you've got all the 50 million pieces around here, and you know, it's a picture of maybe I don't know, a flower or something like that, or whatever it's a picture of, a ship, who knows. Okay? Now, if I ask you, just check if the solution is correct. That's easy. Look at it. Does it look like a flower? Yeah, done. Am I right? Mm. Okay. If I say, great, now here are 50 million pieces. Go. It's going to take you a bit longer than look at it and do it, right? Mm. That's the difference. Some problems are really, really difficult to solve, but when you have the solution and you show people, hey, this is the solution, everyone can see, okay, that's the solution. Does that make sense? That's the kind of problems that they're solving, right? Technically, they're doing problems involving hashes and a prepended number of zeros on the hashes. So you've got exponential difficulty, and you know, it doubles every so often, and blah, 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 blah. All of that detail is probably unimportant as long as you understand that the importance of difficult to solve and easy to check. And because it's difficult to solve, a whole bunch of different miners work on it at the same time, trying to get solutions, right? The first one to solve it pops up their hand, says, hey, in the network, I've got it. And then they take all the transactions that have been submitted to the network, they dump it into that block, okay? And they say, right, this is the new block. And, you know, that block is submitted to other people who verify it, who check, you know, is this actually, you know, the right thing? and once they've checked the solution, they've checked yes, it is the right thing, then they go ahead and add it to the blockchain, and that becomes the new block, and then you start mining another block from that. So far, so good? I mean, I've left out a couple of things like, orphan blocks and, forks and what happens, if you can't decide and two people come up with blocks at the same time and stuff like that. But all those are essentially details, that we kind of abstract away because, they're in the longer scheme of things irrelevant. We can assume this model of how thing works. Okay, so that's how Bitcoin works. Questions so far? Yeah.
So what was the motivation behind Bitcoin?
Oh, to have a decentralized currency, to have a decentralized way of exchanging value between people without having a bank involved. Because let's say, for example, that you want to sell drugs, okay, to other people, okay. Now, how would you do that? Well, it's kind of difficult to, or let's say that you're an arms dealer, and you want to exchange value with someone else who's an arms dealer, or who wants to buy your weapon somewhere else. It's kind of difficult to say, okay, look, here's my bank account and you can deposit money into it, because I mean that's linked to an actual name, and if you just distribute your bank account, then police are gonna say, okay, who's got this bank account, and they're gonna come knocking on your door. You're gonna be the shortest lived arms dealer in the history of arms dealers. Okay, you can't sell many weapons that way. So and part of the reason for that is because there's a bank in the way. And the bank can give away your... Okay. So, please don't take that one out of context, okay? Because that kind of thing actually can get you into trouble if it's taken out of context. But anyway, I mean, I trust you guys to be sensible. In that country, you can't play certain games, you can't read certain novels, you can't buy certain things, etc. Because it's restricted. Okay. Now, if you want to overcome that kind of censorship, if you want to, for example, be able to buy whatever you want from whoever while that person is anonymous and you are anonymous, right? Then an easy way would be to say, you know what? I want to send something from my wallet, which has got the name ZAB34 blah blah blah, to this wallet here, B, which has got the name RXV97B blah blah blah, okay, and so on, and then someone can pay from their Bitcoin wallet to your Bitcoin wallet over here, and then you can convert those Bitcoins into cash at a later date, thus obtaining cash and without needing to involve a bank, and everyone can see the transaction has occurred. So everyone knows it. Everyone sees value has gone from this to this, and this much value has gone. But no one knows who's behind this, and no one knows who's behind that. Yeah.
So it's there to protect criminals.
Well, criminals do use Bitcoin, yeah. Because it's fantastic for that. It's outside the financial system, okay. And it was intended that you can't just go and look behind it and see who's there. Absolutely. So yeah, it's very attractive for criminals, but it's also attractive for other reasons. Like for example, let's say that in Syria or in Egypt there's a bunch of freedom fighters, and of course if you send money into their accounts from outside, people are going to be like, the government is going to, be very upset, and they're going to take them into a pit somewhere and torture them. Okay, you don't want that to happen. You want them to continue. So anywhere where you need to send money anonymously between unknown person and unknown person, Bitcoin is fantastic for that. Does that make sense? I mean, criminals need to do that. A lot of other people also need to do that. So,
where was it founded? Like,
when you say where was it founded, I don't.
where like the roots of everything?
Oh well, in I think 1998 was it? Satoshi Nakamoto, which is an alias. No one knows who Satoshi Nakamoto actually is, or if they even exist. Published a white paper. So in other words, a white paper, just a thing on the internet, was published saying Bitcoin, a decentralized cashless system for cash, or something like that. I forget what the exact title is. And it described, this is how the system will work. These are the guarantees. Here's how, I've proved that this is the case, and here's a reference implementation to say, like, this is actually practical. And if you guys just go and do this, voila, it'll all work together. And that's the roots of it. Yeah.
And now you have to re-engineer the whole system to try and change anything in that, so it has integrity. If you have to try and fake a transaction, you have to redo all the calculations, which is practically impossible.
And then let me explain that. You guys heard me say that the proof of work is really important, right? Okay. Well, let's say we've got a set of blocks. Thank you for bringing that up. That's called the immutability of the ledger, all right? So we're going to call this block n. This is n plus 1, n plus 2, n plus 3 over here, okay? And so now, let's say that there's a transaction in n that I want to undo, that I want to say, actually, that didn't happen, okay? So how do I do that? Well, it's easy. All I need to do is go to this block and mine a new solution, plus a new solution, a new solution, a new solution, because Bitcoin miners will always work on the longest chain of blocks, okay? So, in order to make the longest chain, I need to make a revised this block, okay? Then revise this, and this block, and then one more block to make it the longest, okay? In order to do that, I need to have more computational power than the entire existing network. Because I need, in the time that everyone else will be able to mine one block, right? One block here, I need to be able to mine 1, 2, 3, 4, 5 blocks.
Wait, you mean the current network that's existing?
The current network.
In the world, or
Yes.
in that network?
No, in the current, I don't understand your question. It's one, the Bitcoin, the blockchain is one long chain of transactions.
No, I mean like the network as in the existing network of all, or like the entire world, or that blockchain network?
Of that blockchain network.
Oh, okay.
That blockchain network.
So if you had a supercomputer, you'd be able to...
No, if you had a supercomputer, it wouldn't work anyway.
Oh.
There's no supercomputer that can mine that fast. There are proofs that say that look, basically once it is 6 blocks in, it is effectively unchangeable and immutable forever, because you can use the entire computing power available in the entire world, and you will not be able to make 7 blocks in the time it takes other people to make 1. So when I say it's a hard problem, it's a hard problem. Okay? So that is where the immutability comes from. Of course, if you've got a lot of computing power and it's only 1 block deep, maybe you can make 2 blocks in the time it takes to make 1. Or maybe you can, but the more time goes on, the more immutable it is, the more unchangeable it is. Yeah?
So, like, what kind of problem are we talking about? Because when I think problem, is it maths or is it
It's what's called a computationally infeasible problem to reverse. It's hashing. It's hashing. The problem is this. Okay, I've got to explain something about cryptographic hashes, so if you don't mind me just taking a certain diversion here. Okay, right? A cryptographic hash is something that takes data over here, passes it through your hash algorithm over here, and out at the end comes some small fixed string. Okay, like say 20 characters. All right. Now, if I give it the same character, if I give it the same data and I pass it through, it will give me the same thing every time. Okay, so there's nothing random here. Okay, so a very simple hashing operation you can think of as being, if you give me, if I take every character, and I, take the like every character in computers has got a particular number attached to it. Okay, that it's like its ASCII value or its Unicode value. So I take that and I just add that up. So A plus B plus C. If I have characters A, B, C, blah blah, I just add A plus B plus C, etc. Right? And then I do that modulus 1024. So I've now got a number between 0 and 1023. Right? So now we can give it any size input. It doesn't matter what size of the input it is, right? And we run it through this, and we will always get a number between 0 and 1023. So far, so good?
Yeah, there you go.
No, you got to have this firm, because unless you understand this, then there's no point really. So any size data, fixed size output over here, and this is the hash algorithm over here, right? So I mean, you can think of it as kind of like the analogy. One of them that I've heard is like a mincemeat machine. Have you ever seen one of those? Sort of like you take it and and it doesn't matter. Well, in that case, I guess the more meat you put in, the more mince will come out. But this is a magic one. So the more, it doesn't matter how much meat you put in. When you press the button, it'll go. All the meat will disappear, and only like a gram will appear on the other end. Okay. But of course, then you look at that gram and you say, okay, can I take this and see? All right, were you a chicken originally, or were you beef, or were you lamb? And sometimes it's difficult. Okay. Now, a cryptographic hash is a special kind of algorithm because there are two things that it has, right? One is preimage resistance, and I'll explain that. Another is collision resistance, and preimage resistance. There's also a variant called second preimage resistance, but we'll go into that. Collision resistance means that if I make a tiny change in this here, right, I get a huge change on this side. Okay, that's called the avalanche effect. Okay, so I can just change one bit or one byte or or I can change the whole thing, or I can just, and I get a very huge change on the side. Okay, so it's actually just infeasible for me to find two inputs that will give me the same hash. It's very resistant to collisions. Okay, so the actual possibility of a hash, for example, for SHA-1 is let's see, it's about 2 to the SHA-1 is I think 128. 5 times 32. Is that 128? Do the sum for me, someone.
5 times 32.
No. It's
128.
120. It is. Okay. Wow. So see, I did my PhD on that, and they go away so quickly.
5 times 32.
5 times 32. Okay. Anyway.
One.
Oh yeah, that's 160. I was like, there's something wrong with that. Okay. So thank you very much. It would take 2 to the 80 different hash evaluations before you even had before you started becoming likely to actually get a collision. Okay, 2 to the 60. Now that is a huge number. That's a number that's greater than all of the grains of sand on all of the beaches of the world. Okay, that is a number that is greater than all of the atoms that are in the earth. That's a big flippin' number. Okay, that is a big number. So you gotta do all of those in order. So that's computationally infeasible. Does that make sense? Okay, that's collision resistance. But the second property is the really interesting one, perhaps from our perspective, pre-image resistance. If you give me this, so if you give me this output here, I cannot find an input that will lead to that output. And in fact, that's an even more difficult problem than collision resistance. So its difficulty is even higher than that. So you just can't. Now you might be saying to yourself, surely that there's no such algorithm. Surely you can always go back and find something that comes up with that. In which case, I invite you to try. You can pick any of the standard hash algorithms. Start with SHA-1. I worked on it for 6 years, and I worked on this problem, and I couldn't do it. It's just no, can't be done. But if you do it, walk into my office. I will personally convince the dean to give you a PhD, like at the next graduation ceremony. Okay, I will write up your work myself, and I will give you credit, and we will do that. Okay. All right. So yeah.
I just wanted to know that the security risks, especially with your public blockchain, in terms of when companies want to now publish their statements on blockchain, what are the security risks there?
I don't see any security risks. What security risks do you see?
You mentioned the one that he asked. Of you can't replicate.
Yeah. Immutability, right?
Yeah, and then it also kind of limits. There's only one person has access to the only one that has authority over the blockchain in terms of what information goes onto.
There's no one person that has authority over what information. If you want to put information in, done.
No, I'm saying as in companies that want to upload their stuff onto it, that means that they're the only ones that have the control of what information goes on.
Oh, right. Well, look, the blockchain is public.
Yeah.
I mean, it's not like a magic hammer. Like I tap it, bam, it just works. So I mean, you've got to use it for what it's used for. Okay, it's a public. Okay, I'm just going to write over here. Public, distributed, transparent ledger. By ledger, we mean, it records transactions. So you gave this money to that person. That's what a ledger does in a bank. Credit and debit. Okay. So I mean, if you are trying to store private information there, public. If you're trying to keep it from your competitors, it's distributed. If you're trying to, make sure the public can't see it, or it's transparent, everyone sees how it's working, and I mean, it's just a really piss poor choice.
If you know how companies are required to issue these.
Oh, you mean public statements?
Yeah.
There's no problem. And if you put a public statement on the blockchain, what's the problem? I mean, you intend it to be public, transparent, immutable. I mean, there's no security risk at all of doing that. I mean, I think a new block is mined every 6 minutes or something like that. Something like that, right? So basically, you put it onto the blockchain, and what's 6 times 6? 36, right? About half an hour later, it's basically passed into history, and no one can change it. Okay. An hour later, if you're really, so I mean, if you're really paranoid, in an hour's time, you can go and look and see, is it there? Yes, it is. You're now ancient history. You know, no one's going to be able to go back and modify you to suit you. So yeah, it's great for that purpose. Anyone else? No? All right, now let me talk about smart distributed applications running on Ethereum, okay? And here, I'm going to skip over some changes that might come up in Ethereum, like going to proof of stake rather than proof of work, because they're kind of, you know, they improve the scalability of things, but they're a little bit boring to talk about before they happen, because they're uncertain right now. Anyway, get rid of all of this stuff. Now, I've so far been talking about Bitcoin, yeah? Mm-hmm. And the primary thing that you can put into a Bitcoin block is a bunch of these transactions. Take from this, send to that. So far, so good? The primary thing that you can put into an Ethereum blockchain is code. Okay? Now you've got two different kinds of accounts in Ethereum, right? One of them is, I forget its name, but it's basically the human account. Okay, it's for people. Okay, and people can control it. They can accrue ether. You know, as you mine a block, you get rewarded with a certain amount of you know, of coins or ether or whatever the currency is, you know, which you can then spend. So people on the human account type, you can you know, have ether that you accumulate. On the other account type, it's called a contract account type. Okay, and when you send ether to a contract, then that code starts executing. Okay, so that's what the chain does in respect of that. So in other words, if I send ether to, you know, let's say a contract account type has been established over here, ZB34K, blah, 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 right? That's now a contract account that's been established, you know, after that block. Now, I send so many ether, slight simplification, I'm ignoring things like a gas price and all of that, but I send so many ether to that over there, right? And it goes off and the network runs code for me based on the ether that I send. Okay. And it takes the results and it gives them to me. So far, so good. Okay. So everyone can know, okay, this was run by me, you know, and your code can do various state changes which are recorded in the blockchain. And those state changes basically become immutable, just as it does in the Bitcoin blockchain. And that's what's called a smart contract. And it's a bit of a hyped up PR kind of media name, smart contract. All that it means is that I can write code that if you send it a certain amount, it will do a certain service and change a certain state and then continue on. So for example, if we're going to make a voting application on the chain, we could basically say, you know, when this person sends that amount to this contract here, then increase Donald Trump's vote by this much, or increase you know, Zuma's vote by that much, or increase. I don't know, why am I taking these characters? I must be taking, you know, I must be taking like, you know, Mother Teresa or something like that as my example, you know, because people you'd actually want to properly vote into office. I guess why they're not, that's why they're not politicians, but anyway. And then you know, it records the state change in the chain, so that after I have sent it and it's recorded it and said, yes, I have got this, then a short while later it will be immutable and permanent. Does that make sense? That state will be forever. And that's what a smart contract is, at the basic kind of level. Questions about that? What can you make with this? Anything. Anything you want. Some things, if you run them on the blockchain, then you're a bit of an idiot, really. Because the blockchain is not efficient. It's not meant to be efficient. Okay? In fact, it's one of the most inefficient ways of computing things in the entire world. Okay? Because when I send my ether to there and I say go ahead and compute this, what actually happens is a lot of the miners in the Ethereum network who receive that and choose to process it will actually start processing that. So the same code is running and using up electricity at thousands of different places in the world at the same time. This is an awful way to do things. Okay? Also, they can verify the exact state changes that will occur and put them into the chain. That's just horribly inefficient. That's not parallel, that's just inefficient. Yes?
And if you made it private and have sort of certain miners just as the ones who are allowed to only approve those functions, then it will be very efficient.
Oh yes, absolutely. But if you're going to do that, then you lose a few things. You lose public, you lose transparent, and because there are only a few people on it, you lose distributed. Which means what you have at the end of the day is your computers running code. And if it's only your computers running code, then the computational power of the network is quite small, right? Which means that if, let's say, 2,000 more people join the network, they can easily make the longest chain far faster. And, then all of your things are basically worthless.
You would still be transparent to the people that are within that circle. So
You would be.
A private company would still be distributing if we all agree in this room that we are the people that are meant to see the files.
Mhm.
So it's public-private in this circle, and then ledger as well as it will still be maintained.
You are correct. But on the other hand, you see at a small scale, this is why blockchain doesn't work so well at a small scale. Because at a small scale, like let's say we've got enough people that we're all members of one company in this room, right? Now I'm going to do something weird, okay? I'm going to look all of you in the eye and say, please don't screw me over. Done. And if you do, you know what? We will all collectively take the decision to fire you. Because, and like we know you, I've met you, I know you, you look like a criminal, I know you, and so on, So, in small situations like that, where there are actual human links between people, there's genuinely no need for blockchain, because the people actually talk to each other.
But we won't really know each other. We have those wallet IDs that basically mask us from our true identities.
So you mean you're all communicating from different parts of the globe,
Yes.
and you could do that. Then we're all gonna have everything agreed on, right? And we're all gonna have it all done, and then after everything's been done and I'm in a very advantageous position, I'm going to reveal that actually, I have access to a high performance computing cluster and steamroll over everyone's transactions and be done. The end.
Okay.
You see, the thing is that a small network doesn't work. The immutability is based on the idea that the majority of nodes in the network have got no incentive to be dishonest at all because you don't know each other.
So China could do the same thing to us here.
No, it genuinely is a hard problem.
Okay.
Like China, it doesn't matter if you put all the computers in China working together, once it's 6 blocks deep, that's it. Doesn't matter what you do in China.
Right.
But that's exactly the thing. it's based on differences in computational power, and so it'll never work at a small scale. It can only ever work at a large global kind of level, or at least maybe a national level. It can work at a national level, but anything less than that, and I think you're just asking for China to come in and say, got your currency, have a nice day.
So if we move to proof of stake, would that make it better? Because then I'm pro making it work, so I will always argue to like try and make it work.
Proof of stake will make it better in some respects. Proof of stake is a different way of doing things that is not based on how much work you put in. It's based on taking a risk instead. So in proof of stake, basically instead of basing things on the work, what I do is I say, you know what? I want a chance of being rewarded for performing this calculation. So I'm going to put a bit of my own money into the pot, right? That's my stake, okay? And now the computation is distributed to a bunch of, I guess, almost random people. How many people, whatever, we don't know because we haven't seen the protocols yet, but we'll see. To a bunch of people who have all decided, I'm going to put a bit of money in. And if you faithfully perform the computation, and then you send the result back in, and that result matches everyone else's result, then you get your stake back and a bit of reward as well. Okay, but if your computation doesn't match the majority's computation, then you lose your stake, and you also might lose your part in the network. You might also lose your ability to take part in other kind of transactions like that. So that's it. It's based on, do you want to risk your position here? Do you want to risk your money on this? Whether it'll work or not, that leads to issues of distributed denial of service. It leads to, but you know what? We'll see how it works and how it doesn't, because Ethereum is thinking of moving to it, and 2 years from now, you and I can have a conversation based on how it worked out. Yeah.
It's been partially implemented.
Say what?
It's partially implemented.
Yeah, but you see, until a partial implementation of such a thing counts for nothing, because if you're going to go steal a coin, right? Steal bitcoins, or steal something, a cryptocurrency. Which cryptocurrency are you going to target? Probably Bitcoin. Why? Because it's the most stable, most people have it, or most people who are, it's the most widely distributed one, okay? And sorry, and because it's the most widely available one, you know that if I steal so many coins, the network isn't going to shut down. It's still going to continue on. I'll still be able to redeem this for cash at some later point. Okay. And criminals think that way, of course. There's no point in putting in a heck of a lot of work for I might get a reward at the end of it. Because if you're going to do that, why are you a criminal? You're doing criminaling badly. You should go and do actual work, because that's what actual working people do. They put in a lot of work and they hope for a return, but they don't know they're going to get a return. Okay? I put a lot of work into teaching. Do I know anyone is going to walk away from here the hell that I know. So it doesn't make sense. Until the system is there, criminals aren't really going to target it. And if you've even got two brain cells to rub together in your head as a criminal, you don't want to point out the flaws before it's widespread. No, you want to keep the flaws to yourself. Then, when it's widespread, you want to hit everyone for all they're worth. So, as I say, we will see. And a prototype in this space is basically worthless for that reason. And they're going to have bugs, and we'll see. Any other questions? Okay, well, look, I hope it was sort of useful and explained some things on the blockchain, and you know, whatever questions you came up with or what you wanted to know from this talk, you got an idea to ask and answer and stuff like that.